Yeah. So anyway, yeah, last term I was trying to record lectures for my two math course. It worked. So let's try this for this one here. Yeah, and you have taken my course, so basically we'll use some YouTubes to help you with some assignments and some other problems, right? Yeah. Let's keep with the review here. If you recall in the last lecture, we had one of the graph there talking about those different kind of stress. One is normal, shear, okay, for normal stress due to axial loading, due to bending. For shear, it could be a direct shear. It could be a torsional shear. It could also be a bending shear. Okay, so let's keep going with the review here. For axial loading, the shear is very simple. So that's just basically sigma equal to F over A, right? F over A here. Okay, maybe I should turn on the microphone. It doesn't sound very. Yeah. Okay. So now let's look at this bending shear here. Okay. Sorry, bending normal stress. Is it working? Yeah. Okay. So for bending normal stress, essentially let's use a shaft, for example, here. So let's say, suppose I have a shaft at here, right? And the shaft is subject to certain bending moment. Okay. By the way, during the course or in the past, you have come across with two terms. One is moment, the other is torque, right? So what's the difference between a moment and torque? Can anybody tell me? When do you call it moment, and when do you call it a torque? Very good, very, very close. So you said torque is through the middle. Basically, torques cause what? When the, well, first of all, you gotta understand moment, the torque, they're actually the same thing. Okay, they refer to the same concept. When you call it the torque, when it's causing a rotation or twist, right? And you call it the moment when it's causing a bending. Okay, so that's basically the idea here. And the other thing is, you also need to understand is, it doesn't matter whether it's a bending, it doesn't matter if it's a moment or torque, they all basically a vector. Okay, they all a vector. So let's say you have a bending moment in here, it's actually a vector. I used a curved arrow here to represent this bending moment M at here. Actually, it's a vector. Where's the vector pointing to? Your right-hand rule, right? Right-hand rule. So use this right-hand rule. So that vector is pointing to which direction? To the out of the paper here, right? So that's M basically here. So this z-axis, let's say this is z-axis here. So this bending moment here, sometimes you can represent use M vector. So this M vector could be starting from here up to somewhere here. Let's say representing that moment. Okay, yeah. This arrow here, okay, this arrow here, it just basically represents which direction it's causing the bending or the twisting. Okay, yeah. So here you have two bending moment here because we're talking about the moment here is twisting, it's bending it. Okay. Now let's say this is a y here and this is x-axis. Okay. Yeah. Then if I cut a cross section anywhere here, okay, I cut a cross section here. I'm gonna look at, let's say, look at a cross section. Okay. If I look at a cross section, let's say a front view. This is a cross section here. Okay. Cross section. And the distribution of this bending normal stress due to this bending moment, it's like this. Okay, so it's distributed as this. At the top, it goes this way. At the bottom, it goes like this. Okay, yeah. Now, the value or the formula, okay, this is x-axis, right? The formula for the bending normal stress is sigma equal, okay, negative my over I. Okay, so that's the formula if you recall that. And what are each one of those things mean here? M is that bending moment, and y is the distance from this center head here to where you are interested in. So let's say you're interested in this location, then this portion of distance is y. Okay, yeah. And I refer to is so-called the area moment of inertia. So sometimes we call the second moment of inertia. Okay, so I at here is the second moment of area inertia, or second moment inertia for the area. For the cross section or for the area, okay, doesn't matter. So basically, moment inertia, you can have two different kind of moment. One is mass moment inertia, the other is the area moment inertia, right? Yeah. Now the formula for the I is integral at here y squared dA. So y, because this is y to the neutral axis, to the distance here, and A is the area representing this area cross section here. Okay, yeah. So that's how you calculate the I here. But we usually deal with is a circular section or a rectangular section. So we just have to memorize what the I is for the special kind of a cross section. Okay. Now the other way of saying this is I here, more precisely, this is actually called IZ, because this is moment inertia about this z-axis here. Okay, more precisely. The other thing here, if I write it in IZ, so it can be also written as MZ y over IZ, like this. Same thing. Okay, but you don't really have to write every time a subscript here, as long as you know what you're dealing with. All right? Yeah. So a simple question at here: why do we have a negative sign at here? What's the next sign for?
Differential between compression and tension.
That's right. Where do we have a compression? Here, right? Extension at here. Okay? Yeah. So you can see when you have it at the top there, according to the coordinate system, the y is a positive number, right? So you put a positive number here, you got a negative number for the stress, because the stress at the top is compression. So that's why the negative sign is there. Okay. Again, at the next week tutorial, there will be also today we'll review some of the sign conventions, and this actually sometimes could be quite confusing. To be more precise, a lot of the time you have to be very precise in terms of sign convention, basically negative, positive. But however, in the future, when we do calculation or design, the sign is not that matter, because even if you mix this made a mistake regarding sign, but as long as you can obtain the maximum value or the absolute value, then you're still going to be okay. All right? Yeah. So at this stage, pay attention to the sign at the early stage. Okay. Later part of the course, you can neglect the signs. Okay. So as I said, we only need to care about the specific kind of cross section. Okay. So this is one specific rectangular. This is a circular kind of cross section. And if this is what we call the z-axis is our neutral axis, so z-axis is the so-called neutral axis, right? So the z-axis here is a neutral axis. Okay, and we're looking at, let's see, the IZ for this cross section here. The dimension for the rectangle, this is B, this is H, and this is the diameter d at here. Okay, so here's the formula you need to memorize. Okay, two formulas that you will use, that particular second one. Okay, you probably use that a lot. The first one is 1/12. Okay, BH cube. Okay, first one. So here's a little trick for memorizing the first one here. Okay, because this is the cross section here. So the B, the value B here is the one that parallel to the neutral axis. Okay, the H is the one that perpendicular to the neutral axis. Okay, yeah. So let's say, for example, if this is Y here, then guess what? What will be the IY now? According to the way that I just said it, what will be the IY? Exactly, HB cube. Okay, yeah. And second one here is a circular cross section, and actually really doesn't matter. It's the same value, okay, for any axis going through this center of the circle here, and the value of that is pi d to the power 4 over 64. Okay, over 64. And how these values are obtained is based on this formula here. Okay, so this formula essentially is a double integral, because integrating over the area here, so this is basically a double integral over the area. Right now, this is the area here. Okay, if you carry out double integral, you get this. Okay, yeah. So that's the second kind of stress, bending normal stress. So all you need to know is this formula, but looking at this formula, one fact that you need to always remember is this. You look at this one here, or the way to draw here, basically what it tells us is it's 0 at where? At this neutral axis, right? So basically 0 at the center here, and the maximum at the top and the bottom here. Okay, so maximum is there's a positive one, there's a negative one. Okay, that's one of the one of the basic things that you need to memorize about this bending normal stress at here. Okay, yeah. And the other thing is where the maximum and the minimum really depends on which direction you're bending. See, right now this is the moment here. This is basically how it's being bended, right? Now suppose that you're not really bending this way. Maybe you're going this way, bending like that, right? So basically the direction of the moment is different. Okay, so then the minimum or maximum location changes as as you have a different orientation of the bending moment. Okay, yeah. So just shortly we'll look at the next one here, basically two-plane bending. Okay, so let's see what happens when we have a two-plane bending. And two-plane bending is a very common situation when you design for shaft. Okay. Yeah. So we look at the two-plane bending for circular shaft, okay, or circular bar. Okay, we'll look at this one here. So let me draw let's draw this draw a circular bar at here. Okay, let's see, I have a circular bar here. So we're looking at a two-plane bending. I'm going to draw it in a 3D like this. Okay, so let's nail our coordinate system first. Okay, very similar coordinate system as before. Okay, X, Y, Z like that. Okay, yeah. And now let's apply the bending moment to this bar. So first direction of the bending moment is this. It's just like before, it's bending, okay, like this. Essentially, here's basically the direction of the bending, right? If I draw this bending moment using vector, then it's a vector using right-hand rule. It's a vector in this direction here, right? In this direction, right-hand rule. So let's call this guy MZ, okay, vector. So moment is a vector, right? And the magnitude of the vector representing is basically how big the moment is. Okay, so let's use mz representing the magnitude. Okay, so that's the first plane of bending. And the second one there, let's say it's gonna bend, okay, in the plane of xy. So it's bending it, it's bended like this. Okay, like this one here. Okay, so this guy here is in the plane xy plane here. So let's call this guy. Before we call this guy here, let's draw the vector. Draw the vector representing this bending moment. Right hand rule. Where is this vector pointing to? It goes up, right? Yeah. So in the direction of y. Okay, so that's the second bending moment. So let's call that my as the magnitude. Okay, the magnitude. Okay, so now you have a two bending moment. So that's what we call two-plane bending. And then we're interested is if I cut a cross section here, and how is this bending normal stress distributed across this section, right? The cross section here. Okay. So the way you deal with this kind of situation is, because you got two plane bending here, you got two vectors here. So what would you do? You essentially gonna just exactly add these two vectors together, right? So vector addition here. So the vector addition. Okay, when you add these two vectors parallel, and then you draw this. This is the resulted bending moment due to these two. Okay, so let's call this guy M at here. Okay, call this guy M. Then, because this my and mz are perpendicular to each other, okay, so this is actually a simple situation, then the magnitude of this m will be what? Will be this, right? Will be just my squared plus ms squared. So okay, so this is basically the resulted bending moment. The direction is this. The magnitude is this. So the direction is this. Okay, so now maybe the next question is this now. Where can you find the minimum and the maximum location of the stress, bending normal stress on the cross section with the given information right now? And where would that be? So you have the resulted bending moment here now. And this is a vector pointing this way. Then how does that bending go? How does the bending goes on the shaft, on the bar? Right hand rule. Always remember the right hand rule, right? Yeah. So M goes this way. That's your thumb direction. The curved finger would be the direction of what? The bending, right? The bending. So basically, how is the bar being bended? It's being bended like this, right? Can you see that? So if I draw it on the diagram here, it's going to be bended like this, right? Going to be bending like this. Okay? Yeah. So in other words, if I'm interested in the location of the mean and the max, so what would I do? I can simply draw a line through the center of the circle and perpendicular to which one? To the M at here, right? So I'll just draw it over here. Okay? Then this location and this location with the mean and the max. According to the current direction of bending, this location will be mean or max? Mean, right? And this location will be the max. Okay, so basically this location will be compression, this location will be tension. Okay, yeah. So that's how you figure this out. And what about the value? The value is based on this m in here. So the value for sigma max, because absolute value is the same, so sigma max will be m multiplied by half of this diameter over the cross section's second moment of moment inertia for the area. Okay? Yeah. So we know what the I is because it's a cross section. It's a circular bar, so the I is pi d to the power 4 over 64. And m is this quantity, so let's keep the m as it is, and then d over 2. Okay, d over 2. So simplify it just slightly here. That 64 goes to the top, then divided by 2, and this d cancel 1d out of here. So overall it's 32m over pi d cubed. Okay, yeah. So this is actually a formula you use quite a bit. Okay, giving a bending moment, the maximum bending normal stress will be 32m divided by pi d cubed. And remember the d here is the diameter. Okay, yeah, this formula is for diameter d. Okay, not the radius here. Okay, okay, yeah. So that's two plane bending. Any questions? Okay. So that basically dealt with the normal stress. Then let's look at the shear stress. The first kind of shear stress will be the direct shear. Okay, direct shear. Direct shear is a sort of special kind of shear because that happens only when you have a very sharp, very small cross-section area. And for example, you have 2 plates or maybe 3 plates, doesn't matter. Okay, and bolted by, okay, and connected by a bolt and nut. Okay, so if you apply a force over here, okay, to be in balance. So let's see, this is half force, this is half force, like this. Okay, yeah. And we're interested basically what will be the stress on the cross section of the bolt. Okay, so this is a situation called direct shear. Okay, direct shear. The cross section is very small. Okay, and the two forces are not too far away from each other, very close, like a scissor kind of force. Then the shear, the tau, will be basically the force divided by the area. Now you got to be careful. It's not F over the area. It's what? It's the half force, half of the F over the area. Okay. For this situation. Okay. Yeah. So that's direct shear. Okay. Direct shear. So which will be F over 2A, of course. Okay. That's it. That's direct shear. And the other situation, as we talked about, is one is the torsional shear, and the other is the bending shear. So let's look at the bending shear first. Okay. Let's look at the bending shear, or sometimes we call it shear stress due to bending. Okay. So when does this situation happen? We have to understand when does this situation happen. Okay. Now, let's see if I draw a situation like this. Okay. Here's a circular bar, maybe supported by a simple supported here, and I will just arbitrarily apply certain kind of force on it. Okay, certain force. Yeah. So one of the basics that you're going to get reviewed is how to draw the bending moment diagram, how to draw the shear force diagram across this beam, right? So I think you learned that in 251. So we'll review that next week. Okay, yeah. But in any case, let's see. You probably will get a bending moment diagram, a BM diagram. Okay, just say for example, right? Maybe like this. Okay, who knows? Okay, yeah. the proper way of drawing this one here needs to be associated with certain sign convention. So that will be reviewed. And then you can draw a shear force diagram. Okay, so that might be this, yeah, or up downs like this. Okay, yeah. So what does this two diagram mean? This two diagram basically means if I cut a cross section anywhere, okay, along the beam, then at that location, let's say if I cut it over here, then when I look at that cutting location, then there's going to be a bending moment and there's going to be a shear force V over there. Okay, so which can be derived using equilibrium equation. Okay. So that's basically the general situation for a beam like that. So then here comes the question now. So you look at this cross section here, there is a shear force on the cross section over there. Then we will have the so-called bending shear, okay, due to this V at here. Okay, so this is why we call bending shear at here. Okay, so the beam is under bending. Okay. So this bending shear tau, right? So the tau is due to the V there. Okay, due to the V. Okay. So of course, if there's no V, then there's no tau, right? So if V is 0, then the tau is 0. Okay, so this is one of the things I mentioned in the last lecture. So some situation is even if the beam is under certain loading, but however, for a section of the beam, there is no shear force, and that's the situation. Remember what we call that? A pure bending, right? A pure bending. So just give you an idea what's the pure bending situation. For example, if you have a guy doing weightlifting, okay, right? If your guy's doing the weightlifting at here, and of course they have same weight on the both sides there. So let's say this is W and W at here. If I do a free body diagram for the beam, and that beam will be a force WW over here, right? At the same time, because you're lifting it, so you're supposed to grab it symmetrically, not tilted. So basically here the two distance here are the same, and you will have a two lifting force, and up here, right? Up here. Okay. So this two same, and the 2W and the 2F will also be the same. If you carry out this F will be the same as W at here. Okay. Yeah. So then, if you draw a bending moment diagram and a shear force diagram for this beam, and you will see that the shear force if you draw a shear force diagram, if you cut it here, okay, then there will be a shear force going up, right, to balance it. Okay, so going up is actually negative when you draw the shear force diagram. So the shear force diagram will be, okay, negative, up, 0, up, positive, up to after here. Okay, like this. Okay, so your practice is in the next week tutorial. Okay, so negative W here, W here. So in the middle, between basically this for this section here, it's 0. Okay, it's 0. And if you draw a bending moment diagram, okay, this is V here. If you draw a bending moment diagram, that will be. Let me see. Let me see. This is negative here, so that will be more or less like this. Okay. Okay, the bending moment diagram will be looking like this one here. So during this section at here, the only thing that exists is what? Is this bending moment. So that's why it's called pure bending situation. Okay, yeah. And there is a relationship between bending moment and shear force, which is what? The V equal to this x-axis, let's say dm over x. Okay, yeah. Okay, so just remember there is a pure bending situation. Other than that, if it's not pure bending, there might be a shear force. If there is a shear force, then you will have the bending shear stress. Okay, so the only question is, if I'm giving cross section and here, okay, giving it a cross section, how does the bending shear stress distribute along that cross section due to the shear force V? Okay, yeah, shear force V. So the formula for that is, given the cross section here, you're probably interested in the shear stress at the different locations, right? You might be interested in this location, or this location, but there is one situation, right? This is, let's say, this is your z-axis, the neutral axis at here. Okay, there's the neutral axis. Okay, the general formula, okay, the general formula is tau equal to VQ over IT. Okay, VQ over IT. You don't need to remember this one here. Okay, you don't need to remember this one. V is a shear force. I is the second moment of area, and T, let's say you're interested in this location. T is basically the thickness from here to here. This at that location. Okay, at location. And Q is called first moment. Okay, first moment of that area. Okay, not the moment inertia. It's the first moment in area. Okay. So we don't need to go into the details here, but I do need to memorize two things though. Okay, the thing you need to know that is, okay, for the distribution of the shear stress, it's very important. Okay, it's minimum at the top and the bottom. Okay, so basically it's actually 0. Okay, it's a 0 at the top, bottom, and it's maximum, okay, at this neutral axis location. Okay, neutral axis location. All right, yeah. So that's what you need to remember, huh? The fact about the shear bending shear stress. So if I look at the cross section here, the distribution of this. Let me draw this here this way here. If this is a cross section, the 0 here and start to increase, and biggest at the neutral axis location. Okay, so here's basically the tau we're talking about here. Okay, the shear stress. It's maximum at the location of the neutral axis. Okay. And that applies to every kind of a cross-section though, right? Yeah. So then, here's basically the question, what will be the value or the formula we should know about that rectangular and a circular kind of cross-section, right? Yeah. Okay, so here is this first word for a circular kind of cross-section, sorry, the rectangular cross-section. Maximum location is again is at the neutral axis, so the tau max, okay, at this location, okay, is 3 over 2 V over A. So memorize, right? Yeah. Okay. Yeah. If it's to have a circular kind of cross section, and that tau, which is at this location here, will be 4 over 3 and V over A. Okay. So those two formulas, you will use that, particularly the second one maybe. Okay, you probably use that in quite a few situations. Okay, particularly in design for the shaft. Okay. Yeah. So now you think about the difference between the bending shear and the bending normal, right? And the bending normal, where's the maximum? It's here and here, right? Here and here. But 0 at here. Okay? Yeah. But for shear, bending shear, it's 0 at the two locations here. But a maximum over here. Okay? Yeah. Okay? Yeah, so that's bending shear. Okay, so bending shear and then torsional shear. Okay, torsional shear. Any questions so far? Yeah, this is jogging your minds here. Okay, so torsional shear, it's when you have a bar and then the bar is under kind of a torsion, for example, like this, a torque. So again, torque is like a moment. And now we call it torque is because if apply this thing to the shaft, it tends to rotate it. Okay, yeah, rotated about its center, the rotation at the center of the axis. So let's say call it T here. Okay, so technically again it's a vector, but if I just look at the magnitude, it'll be just T, right? It'll be just T. Okay. So right hand rule, did I draw it right? And actually no. So right hand rule, right? So if I draw it this way, the T should be where? Yeah, should be going into it, right? So let's say just change. I'll just change this. Change the arrow at here. Okay, change the arrow here. Okay. So what will be the torsional shear caused by the T? Essentially, the T will cause a shear across this section at here. Okay, across the section. Yeah. Now, if I look at the cross section at here, let's see if I'm looking at location over here. Okay, we can location here. Yeah. Then there will be a tau caused the shear stress caused by the T, and the formula is T and rho over J. Okay, T rho over J. And what is rho? Rho is the distance from the center to where it is. Okay, to where it is. So this is the rho at here. Okay, and of course, if I pick the location right at the edge, the rho will be basically the radius, right? The radius there. Okay, yeah. And what about the J now? Right, this is not I, this is the J. So J is called polar moment of inertia. Okay, polar moment inertia for the area. Okay, yeah. Yeah. So first year, when you learn moment inertia, basically. You have a moment inertia maybe about the certain axis, right? And then you also have a moment inertia about the axis going through origin, and that's basically the polar moment of inertia for the for J. All right, yeah. And J is calculated. General formula is a double integral, and R square and dA. Okay, and R essentially is the distance from a location to the center, right? Yeah. Okay, that's how you calculate J. Now, for a cross section like this, right? Let's see if I draw it here. So I will let you practice. Suppose my torque is this way. Okay, suppose the torque is this way. And I'm interested in, I'll draw it a little bigger here. I'm interested in, can you draw the shear stress? Draw the direction, right, due to this torque. Let's see here, or here, or here, right? How would you properly draw that? The torque is that way. So let's see if here, how would you draw the tau there? Should I draw the tau like this? Do you understand what I'm trying to see out here? Yeah, right, yeah. So the reason I'm saying it this right here, because basically later you're going to have to draw the stress element. Stress element is based on the loading condition, and that has to be properly drawn in order to have a good analysis, right? Yeah. So how do you draw that is, because the T is this way here, right? The T is this way. And the tau, or shear stress, is basically tangent to the surface. So you need to draw the shear stress tangent to the surface, and And at that moment, because this is location here, basically it's been perpendicular to the line there. Okay, yeah. And if I want to draw it here, okay, it's going to be tangent to the surface and also perpendicular to the location of the line there, right? If I draw this, so that's be the tau over there. Okay, yeah. That's how you properly draw the tau, though, right? Yeah. Sigma is kind of easy. Sigma just perpendicular to the surface, right? Yeah. So that's tau, right? That's tau. Now, what's the value of the tau? Is a T rho over J, right? T rho over J. Okay. So now let's take a look at some special value of the tau out there. Okay. First, for a special value for the J for circular, okay, section, that J, okay, equal to pi d4 over 32. Okay. No, I need to be a little bit careful here. It's pi d4 over 32, and d is the diameter. Okay, d is the diameter. Okay, not the radius, it's the diameter. Okay. So let's say if I have a shaft of a diameter of d, according to the formula, right? According to the formula, what would you expect? Where would be the maximum torsional shear stress? Where would be the location of the maximum torsional shear stress? On the surface. Actually, you should see that on the edges here, right? Yeah, on the edges of this surface here. Yeah. Okay. And at the center will be 0, right? It will be 0. So basically, the distribution is more of like this, right? Will be this. On the other side, increasing like this. Okay? Yeah. So that's the distribution of the shear stress due to a torsion. Okay? Formula-wise, you need to remember this T rho over J. So if I'm looking at the tau max for this situation, it will be T multiplied by D over 2 and over that pi d4 over 32 for a circular section. Okay, circular section. So then do a little simplification here. It will be 16t over pi d cube. Okay, pi d cube. So if you compare this one with the previous bending shear, it's very similar, right? Very similar. But that one's 32. This is 16. But we use m over there, but we use t over here, right? Yeah, that's the difference. Okay. Any questions? All good? So this basically covers the different cause for a different kind of stresses. Okay. Yeah. Okay. So we're gonna make use of this simple knowledge later, right? Yeah. But next question is, okay, let's look at the general state of stress. And also we're going to look at the transformation of the state of stress. Okay, so general state of stress, essentially, I think if you recall that, I draw a state of stress for stress elements at the beginning of the lecture last time, right? Basically, if I have x, y, z coordinate system, okay, if I'm going to draw a stress element, so we usually represent the stress element using a cube. Okay. Then you have 6 sides, and then you need to basically put down these stresses on each one of the surfaces. Okay, each one of the surfaces. So this is sigma x, sigma y, and sigma z. Okay, so we can just draw 3 sides. It's good, and the other 3 sides are symmetric. Okay, and then you have here, 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 and here, here. Okay, shear stresses on the surface. Okay, yeah, shear stresses. So for this one here and these two, basically we call that tau xy. Okay, or Yeah, or more precise, but this is okay. And more precisely, this is tau yx, but they're the same thing, so we just call it tau xy here, okay? And these two pair, okay, are called tau yz or tau zy, okay? And these two pair tau xz, okay? Yeah. So that's the general state of stress, okay, in 3D situation. Okay. However, in a lot of situations, we simplify. We look at this a 2D, right? We look at the 2D state of stress. So this is a 3D state of stress. Okay, this 3D state of stress. Now we do have this simplified version, which is the 2D state of stress. So 2D state of stress essentially just for if we simplify, just based on the 3D one, looking from the top, looking from the front view. Okay, the front view basically looking at the view in the XY plane. Okay, that will be basically the 2D state of stress. Okay, yeah. So let's see. I have a. If I'm looking at the front view, I only see a rectangle now. So this is X, this is Y. So you have basically sigma X here, sigma Y here, and then two things, tau XY like this, right? Tau XY. So that's 2D state of stress. Okay. Yeah, so sometimes the loading doesn't necessarily always give you a 3D one. They give you the loading. You take a stress element. They're only 2D is enough. Okay. Yeah. So that's 2D state of stress. Okay. So now comes the question. Now, if you recall that you have this state of stress. Okay. Let's use the 2D one for example here. Okay. You have this state of stress here, which maybe have sigma x, sigma y, and tau xy at the same time. Okay. Yeah. Now, if I rotate these elements, essentially, this is the elements you're taking here. So then what happens if I'm looking at the different orientation, right? If you rotate these elements here, okay, then the state of stress on the surface area here will change, right? It will change. Okay. The only question is how does it change? Okay. However, we do know that. Okay, one of the possibilities is when you orient, basically when you rotate this guy about the z-axis, right? Z-axis out of paper. At a certain orientation, the tau xy is gone. All you have is sigma x and sigma y. As a matter of fact, at that location, okay, you have the so-called maximum sigma x and sigma y. Do you remember that? Right? That's what we call the what? The principal normal stress, right? Principal normal stress. Okay, so if rotate, okay, about z-axis, okay, of a theta angle. So the way you rotate theta angle, remember, huh? It's always counterclockwise as a positive theta, right? Counterclockwise. So if you rotate about theta angle here, then we have these two situations. Okay, we have two situations. Case number one, or situation number one. Okay, at certain theta. Okay, at a certain theta, the tau is gone, so the tau xy is 0. Okay, tau xy is 0, and the sigma reach maximum. Okay, sigma is the maximum. So this is what we call the principal normal stress. Okay, principal normal stress. And the formula, okay, is sigma 1, 2, okay, equal to sigma x plus sigma y over 2 plus minus sigma x minus sigma y over 2 squared plus tau xy squared. That's the formula. Okay. So if you orient it about certain angle theta, then maybe we don't know yet, but we do have a formula for that. Okay, then we can reach a certain kind of state of stress that tau is 0 and sigma is the maximum. We call principal normal stress. So principal normal stress, there are two. Okay, one is sigma 1 and one sigma 2. So apparently the plus sign give you the bigger value, right? The minus sign give you this smaller value. Okay, that's the principal normal stress. Okay, the second situation is, okay, if you keep orienting again at certain theta, okay, the tau, okay, reach max. Okay. The shear stress reach the max. So the shear stress on the cross section becomes maximum. This when tau reaches max doesn't mean the sigma is 0. Okay, yeah. So we only see we don't write sigma equal to 0. Just see tau is max. So what's the tau value? And the maximum value for the tau? Okay. Okay. It would be sigma 1 minus sigma 2 over 2. Okay. That's the plane state of stress. Okay. If you wanted to write this thing out, it's basically positive and negative, the second quantity there. Okay, that's tau max. So those are two special situations when you orient the state of stress element. Okay, a general state of stress element. Okay, this is actually quite important. Okay, very important. Because why? Because this is why. You have let's say you have a shaft under loading. Okay, so let's say for example, right? We'll take a look at some examples later. Let's say you take a stress element at this location. Okay, and you draw the state of stress on that element. Okay, right? And when you draw the stress on the element, you calculate the stress probably based on the loading condition. Maybe there's bending, maybe there's a torsion, right? So you calculate based on the formula that we just showed. Okay, we just showed there. Okay, and then comes the next question is, okay, you calculate, you find certain value, right? But then only the tricky question is, what will be the maximum value, right? The maximum value doesn't necessarily just stay there. And the maximum value actually should be coming from here, right? Should be coming here. So basically, the maximum stress, maximum normal stress or maximum shear stress is probably after certain orientation of that stress element. Okay? Yeah. So your purpose, in terms of design, number one is always to find the maximum stress at or inside this element, the material. Okay? Because remember, when we talk about safety, what do we compare? We compare with the strengths. We compare the strengths with what? With the strengths with stress, right? We compare the strengths with the stress. Strengths you can't change. That's a material property. So when you compare strengths with the stress, you have to compare the strengths with what? With the maximum stress. So how do we find the maximum stress? Here's one clue at here. Okay? Yeah. Okay. So these two formula you better try to memorize. They're actually quite simple to know that. Okay? Yeah. You use that quite a bit. Okay, so now there's a sign convention got involved here. And then I'll talk about Mohr circle. Okay? So sign convention. So here is a state of stress. Let's see, I'll talk about 2D and here. Okay, 2D. Now when do you call it positive and when do you call it basically negative? Alright? Here's XY here. Okay? Yeah. So this rule applies to both normal and shear stress. Okay? So a normal or shear stress is positive, okay, is positive if it acts on positive face and pointing to positive direction. Oops. What happened there? Positive direction of axis. Okay? Yeah, so that's the rule here. It's positive if x on the positive face and pointing to positive direction of axis. So that's probably more confusing now. What is positive face? What is positive direction of axis, right? Yeah. So positive face, there are only two positive face. Positive face is, this is positive face, and this is positive face. Okay? Yeah. And these two are called negative face. Okay, these two negative face. Okay. And what about positive direction of axis? This is positive action directions. This is positive axis. Okay? Yeah. So which means if I have a sigma pointing this way here, right? That's positive. Okay? Let's see. This is 55. Actually 55. Okay? So it's acting on the positive face and pointing to the positive direction of this. It's positive. All right? Yeah. If I have a shear stress going up like this, okay, and this shear stress going this way here, so according to the rule, sign convention, we would consider that as a what? Positive, right? Yeah, because it's pointing positive. Okay? Yeah. However, I need to warn you now, the Mohr circle has slightly confusing in terms of sign convention. Right now, just remember, this is the positive sign convention for shear stress and the normal stress here. All right? Yeah, that's how you differentiate the positive. So sometimes, to be complete, you can add the other side. A normal or shear stress is positive. It's acting on the negative face and pointing to the negative direction of the axis. Okay? Yeah. All good? So now let's talk about Mohr circle. So the Mohr circle basically comes from the idea of the orientation here, right? The orientation. So it appears that when we orient the stress element with a different angle, we got a different state of stress, right? So it's definitely a good idea to have a general approach to give us the ideas or the values of the state of stress after certain orientation, right? And the best way to do that is through the Mohr circle. Okay? So I'll show you very quickly how would you do that using Mohr circle. Did you learn Mohr circle? Yeah. Okay. Good. So for Mohr circle, okay. Again, first, it's a circle, right? It's a circle. It's a circle on the XY coordinate system, but it's actually not XY coordinates. It's on the tau sigma coordinate system. Okay, tau sigma coordinate system. So then, first thing is sign convention. Okay, sign convention. So this sign convention here, you need to be careful with the sign convention we just said there. Number one, okay. So the whole idea is we're gonna try to put down some points, right, in this coordinate system. Okay. So you need to know what's positive and when it's negative in order to put down the points, right? Yeah. So what do we do is the sigma x and sigma y, okay, they are positive, okay, if tension. Okay. So if it's a tensile stress, we're going to consider them as positive in this tau sigma coordinate system. Okay? Yeah. And for a tau xy, for this guy here, okay? For the tau xy here. Okay? So the tau xy, that's different now. The tau xy, we consider it as a positive, okay? If it causes clockwise rotation of the surface. Okay, basically, it consider as a positive is if it's causing or if it has a clockwise direction. So what does that mean? That means here. Now look at this one here, right? So let's say, for example, right now for the sign convention of a general normal and shear stress, and these two consider as what? As positive, right? Yeah. However, now when it comes to Mohr circle, so what do we have here? We have a positive phase here. We have positive phase here. For this positive phase, this shear force goes up. And what direction is that? It's counterclockwise, right? Yeah. It's counterclockwise. Then this guy here will be considered as a negative when it comes to the Mohr circle. Okay. And this guy here is a clockwise, so that will be considered as a positive here. All right. Yeah. So then, if sigma x this way, if sigma y this way, so both are tangent in this case here. So sigma x, sigma y are both going to be considered as positive. So the pair, these two pair, sigma x tau xy, sigma y tau xy, will give us the points on the Mohr circle. Okay, give us the location on the Mohr circle, and that's how we're going to nail down our proper Mohr circle. All right? Yeah. So here's a procedure. Number one, draw the axis. Okay, that we done there already. Okay. Number two, okay, mark sigma x and sigma y. Okay, sigma and sigma y on the sigma axis. Okay, on the sigma axis. So maybe I'll use a specific example here. Okay, specific example. Let's see. I have a shear. I have a state of stress like this. So sigma x equal to 30, sigma y equal to 10. Let's see. Okay. Yeah. Maybe 10 ksi or 30 ksi. That's fine. And we have tau xy at here. Maybe it's 5. Okay. Yeah. So now I'm going to try to draw these Mohr circles according to the procedures. So draw two axes. One is sigma, one is tau. Okay, one is tau. So first step, mark the sigma x, sigma y. So where's sigma x? 30, right? 30. So let's see, this is 30. Where's sigma y? 10. So sigma y 10. So 10 here. So this is sigma x and sigma y like this, right? Okay. Yeah. Second step. Okay. Mark. Okay. A point A for this point. Okay, for this. So mark a point A based on the coordinate sigma x and tau xy. Okay, based on this. So here is this sigma x. Here's tau xy. Now this is basically where you need to use the sign convention for the Mohr circle. So for the Mohr circle, if you recall that because it's 5, so where is my point A? According to the Mohr circle, my point A should be where? Should be somewhere here or here? Where will be the point A? Up top, bottom, right? Bottom, right? Yeah. Because why? Because the tau xy is counterclockwise on that surface. So your point A is actually somewhere here. So it's a 5, right? Yeah, 5 is half of that. That's a little bit out of a proportion now, right? Yeah. So anyway, so let's see. This is point A here. Okay. Let's see. This is point A. Okay. And what's this value here? And that's 5, but it's -5, right? It's -5. Okay. Yeah. Okay. Was that good? Yeah. So third step, it could be slightly different variations here. Okay. Third step you could be is you draw another point B. So you could have a point B for sigma y tau x y. Okay, you could do this. Yeah, you could do that. So if I do that, that'll be 10 and 5, so it'll be here, right? So that's B. Okay, that's B. Okay. Yeah. And then the next step is you connect the point A and B. Okay, connect the point B, A and B. Okay. And it'll intersect on the sigma axis at here. Okay, and it's actually guaranteed that the intersection point is the middle point between 10 and 30. Okay, it's going to be guaranteed like that. Okay. So the last point, so find the intersection point, right? And find intersection point. Let's say now you call this intersection point O. Okay. Then you draw the Mohr circle with the radius of half of this AB at here. Okay. So you draw the Mohr circle in the end. And make sure that passing through both points A and B, right? Point A and B. Now this is a Mohr circle you end up with based on the state of stress. Okay? Yeah, it's very simple. However, you got to be careful though. Don't make the mistake of sign here. Well, technically speaking, actually you see now, right? If you mixed up the signs for the tau x y here, you got the same circle, right? You got the same circle. However, every information you derive from the same circle, you appear to be the same circle from the circle, is all wrong though, right? Yeah, so that's where you need to be careful. Okay, so based on the circle here, okay, based on the circle, let's see what information do we see at here? Okay, what information? First of all, the circle will intersect the horizontal axis with the 2 points, right? With 2 points. Okay. Yeah. Then for this point, let's see, this is C, this is D here. So the C point, at the C point, what's the value of the shear stress? 0, right? Yeah. At the D is also 0. So the C and the D point actually represent is what? It's the principal normal stress. Okay? It's the principal normal stress. Okay? So the C and the D there give us this principal normal stress. Okay? So C apparently is the larger value and D is the smaller value, right? D is, yeah, that's right. Yeah. Okay? And the next question is, what will be the maximum shear stress? Is where? It's the top or the bottom here, right? So you draw basically, you draw something here, that'll be the tau max here, right? Tau max. Okay? So this is the neat thing about this Mohr circle. You can easily find the information that you need to know at here. Okay? The third information is this. The third information a lot of time has something to do with instrumentation. So see, this is the state of stress A and B, right? A and B in here. Now you look at this C at here. So C is the principal normal stress, and this is basically the state of stress, current state of stress. Okay, current state of stress. And this is a C here, principal normal stress. Then the question here would ask is basically, how would you orient the current state of stress so that you can end up with the principal normal stress there? Or in other words, how would you rotate these elements? How much angle would you turn clockwise or counterclockwise so you end up at this principal normal stress, right? That can be easily told by this Mohr circle. So how do you know that? So you orient basically from A to B, so you basically want to rotate from A to C here, right? Rotate A to C. So when you rotate from this A to C, guess what? What kind of rotation from here to here is? It's clockwise or counterclockwise from A to C right now? counterclockwise, right? Counterclockwise. So in other words, you have to rotate these elements counterclockwise. By how much angle? By not this much angle, by half of this much angle. This angle here is, let's say, the theta p here. So the theta p over 2. You rotate half of that angle. Okay? You end up with the principal normal stress state. Okay? So that's the Mohr circle. Okay? Yeah. So orientation, or in our application, okay, most of the time, what we're interested is the value C and D, or the value of the tau. So we're not really interested in how much rotation that you should do to end up at that value. Okay, yeah, most of we need to know is the maximum. But however, for instrumentation, sometimes for failure analysis, to explain things better, it's useful to know that how this rotation should be done. Okay, should be done. Okay, so any questions? All good? Yeah, we're a little bit behind here. I remember I finished all the review now today, but somehow I still got some here. So let me give you an example here. Okay, let's say give you an example. Okay, and I'll have a little bit more example in the next lecture. Okay, but this is a simple example here. So I have a bar right here subjected to pure bending. Okay, subject to pure bending. So there's no shear force in this segment. There's only a bending moment. Okay. Now I'm gonna cut a cross section at here. Okay, let's say cut a cross section. So if I look at the cross section, okay, like this. Okay, so then we're gonna take a stress element at this location at the bottom here. Okay, so let's take a stress element in the bottom here. So we take a very small area at that location. Then we draw a stress element, okay, at that location. Okay, so this is the small area. So what you do is, okay, you basically I'll explode this up a little bit here. Okay, so this is what that little area is, right? What that little area. When you draw the state of the stress elements, essentially you extend that into a cube. Okay, into a cube. Okay, and now you draw the stress, right? You draw the stress on the surfaces of this cube. You draw the stress based on the loading, right? Right now, how many loading? There's one loading M. And remember, what does M cause? What kind of stress does M cause on the surface? Bending normal stress, right? Yeah. So where is the bending normal stress acting on? Which surface? It's that surface here, right? That surface. And according to the direction M, so the bending normal stress will pointing out, right? Will be pointing out. And on the other side, there's also sigma. So do we have anything else? There's nothing else, right? There's only loading, so that's basically the only stress on that element. So this is actually a plane stress, right? Because why? If I look at from the front there, all I see is this, right? All I see is this. That's a plane stress, okay? So this is the plane stress. So now, what would be the Mohr circle based on this plane state of stress? Okay, right? So can you draw the Mohr circle with the procedure that we just gone through? Okay. Okay, first draw the sigma and the tau. Look at this state of stress that is here. So first step is to So actually, first of all, this sigma here is the sigma x, right? And the sigma y here is actually equal to what? 0, right? Yeah. And there's no tau xy. So the first step is to nail down the sigma x and sigma y. So the sigma x is sigma. So this is sigma somewhere here. Okay. And by the way, what's the value of sigma? We just derived the formula. According to the formula is what? M C over I, right? C is half of the diameter, right? Yeah, so that's how you derive for the value of sigma, right? Okay? Yeah. And then the other side is 0, so this is 0 here, right? 0 here. Okay? Then you because your tau is also 0, so the coordinates for the A and B actually just here and here, right? Here and here. Then find the middle points and draw the circle. There. That's the Mohr circle, right? That's the Mohr circle. Okay? Yeah. So if this is the Mohr circle, then the next logical question here is, okay, how would you orient this one to reach the maximum shear stress?
45.
You had to see it specifically. 45 degree, which direction? Counterclockwise. So basically you want to rotate from here to here, right? Yeah. So from here to here, that's you reach tau max. And from here to here, it's 90 here, and divided by 2. So you rotate this one by 45 degree counterclockwise. So basically, it's going to be somewhere like this, right? To reach the tau max. Okay? To reach tau max. Okay? Good. This is an improved here because next lecture I'm going to ask you, we'll look at different situations. For example, I'm going to look at a situation like this one here. Okay, so we're not going to do this, but we'll just look at the situation. Let's say I have a bar here. Okay, I have a bar, and I'm going to subject the bar to a torque. Okay, I'm going to subject the bar to torque. So you in your second year you did a tensile test, right? Let's say I'm doing a torsional test. Okay, so basically doing this. Okay, doing this, and this happened to be a brittle material. Okay, this bar is built with a brittle material. So with the experiment, you will see that it's gonna break like this. Okay, it's gonna break like this. So then the next question is, why? Why is it gonna be breaking like this? And why it doesn't break like this? Right? So that will be able to be explained by the Mohr circle. Okay? Yeah. Any questions? Yeah. All good? Okay, we'll see you next week. I'll keep you guys posted on the tutorial next Tuesday because I still haven't got a TA yet. And we'll see how it goes next Tuesday. Okay? Yeah. Yep. Just a second.